This rock looks worthless, no sparkle, no crystal, no obvious sign of value, but sometimes the most important part of a rock is the part you cannot see. Sometimes the rock itself is not valuable, but one tiny grain inside it can point towards something much larger. Sometimes a rock can carry material from deep inside the earth. Sometimes a gemstone is trapped in a seam so thin one careless cut could destroy it. And sometimes the rock is only the final chapter of a geological process that began millions of years earlier. Cavity, kimberlite, ironstone, volcanic terrain, red garnet, 5 ugly rocks, 5 completely different geological stories. Some can hide opal, some can reveal clues connected to diamond exploration, and one may look like nothing more than a worthless piece of stone. But to a geologist, it may be the beginning of a much bigger discovery. Let's begin. Rock number 5, the hidden chamber. The first rock gives you the most direct question in prospecting. What is inside? From the outside, it may look completely ordinary, dark, rounded, weathered, heavy, but sometimes the surface is only a shell. When molten lava cools, gas bubbles can become trapped inside it. The surrounding lava hardens, the gas escapes or contracts, and a cavity remains. At first, that cavity may be completely empty, but later, mineral-rich fluids can move through the surrounding rock. Silica enters the space. Minerals begin to accumulate, slowly, layer by layer. Over enormous periods of time, an empty cavity can become lined with crystals, quartz, chalcedony, agate, and in certain geological environments, opal. The outside may reveal almost nothing, but the interior can preserve a record of the fluids that once moved through the rock. This is the moment collectors want, but it is also where mistakes begin. Not every rounded volcanic rock contains a cavity. Not every cavity contains crystals, and not every crystal-filled cavity contains gem-quality material. The surrounding geology matters. At Opal Butte in Oregon, for example, opal occurs in rhyolite geodes known as thunder eggs, but only a fraction of the material contains gem-quality opal. So before the strike, there is always a question. Is this simply a rock? Or is the outside hiding a geological chamber? Sometimes, the answer is hidden behind a few millimeters of stone. The rock began as molten material. Gas created the cavity. Fluids entered later. Minerals accumulated. And a geological process lasting millions of years was sealed inside something that looked worthless. The most valuable part of this rock may be the part you cannot see. But our next rock is different. You do not break it open to understand its importance. You follow its journey. Rock number 4, the deep earth courier. This is a tiny mineral grain, small enough to disappear between your fingers. Now watch where the story takes us. Some volcanic rocks have traveled through a geological journey that ordinary surface rocks never experience. Deep beneath the surface, diamonds can form under enormous pressure, but they cannot simply remain there and appear in a field. They need transportation. One important geological transport system is kimberlite. Kimberlite magma can rise rapidly from great depths, carrying mantle-derived material upward. When that volcanic system reaches the crust, it can form a pipe-like geological body, and that body may become a target for diamond exploration. But a dark volcanic rock is not automatically kimberlite, and kimberlite is not automatically diamond-bearing. The appearance is only the beginning. Geologists look at the geological setting, the chemistry, the mineral assemblage, and the evidence preserved inside the rock. Pyrope-rich garnet, chromium diopside, ilmenite. These minerals can provide information about the geological environment from which the volcanic material originated. Not a guarantee, a signal. The richest diamond pipes can still contain an extremely small amount of diamond compared with the total volume of rock. So diamond exploration is not find dark rock, break dark rock, find diamond. It is a geological investigation, mapping, sampling, mineral analysis, geochemistry, geophysics, and eventually testing the geological system itself. The rock may be ugly, but its history may begin deep inside the earth. And now we move from a rock with a journey to a rock with a decision. Because in the next one, the wrong cut can destroy the very feature you are looking for. Rock number 3, the boulder with a secret seam. This boulder looks like rusted iron, brown, heavy, rough, almost metallic. There is no obvious gemstone, no clean crystal, no bright flash. But the question is not, where is the gemstone? The question is, where should this boulder be cut? In some opal fields, precious opal occurs inside ironstone, not as a large crystal, not as a perfect cavity filling, but as a seam, a fracture, a narrow geological pathway. Water moves through the geological environment. The water carries dissolved silica. Fractures create pathways. And over time, silica accumulates in those spaces, in the right conditions. Precious opal can form. The ironstone may dominate the entire boulder. But a thin line can contain the material that transforms it. Blue, green, orange, red, a flash of color inside a massive brown rock. But the color may not run in the direction you expect, and that creates a problem. Cut here, and you may expose the seam. Cut there, and you may destroy it. This is why evaluating rough opal is not simply about finding color. You need to understand where the seam is, how thick it is, how stable the material is, what direction the color runs, and how much host rock should remain. The gemstone may represent only a tiny fraction of the boulder. But that is precisely what makes the discovery so dramatic. The value is concentrated, not evenly distributed. The entire boulder can look ordinary, while one narrow geological boundary contains the most important material. And this brings us to a completely different kind of opal story. The next rock is not mainly about cutting open a hidden seam. It is about the geological process that created the opal in the first place. Rock number 2, the volcanic recipe for opal. Millions of years ago, this landscape was not quiet. Volcanic activity shaped the rock. Lava cooled, fractures formed, and the geological environment began to change. The rock itself may eventually become dull, pale, weathered, ordinary. But the process does not end when the lava cools. Water enters the landscape. It moves through fractures. It interacts with minerals. And in some geological environments, it can transport dissolved silica. The chemistry changes. The fluids move. The spaces become filled, and slowly, the conditions necessary for opal can develop. In Ethiopia's Wallo region, opal occurs in volcanic rocks formed through a complex geological history. Some material displays intense play of color. Some can also show hydrophane behavior, meaning its appearance and transparency can change when it absorbs water. But the color is only the final result. The real story happened earlier, in the volcanic rocks, in the fractures, in the fluids, in the chemistry, and in the conditions that allowed silica to accumulate. The flashes of color come from the internal structure of precious opal. Tiny silica structures interact with light. When the arrangement is suitable, different wavelengths are diffracted: blue, green, yellow, orange, red. But this is why geology matters. Two rocks from the same broad region can look almost identical, yet only one may contain precious opal. The visible rock is not the entire story. The geological process is. And now, we reach the smallest clue on the list, a mineral grain that may have almost no value as a gemstone, but can become important evidence in the search for diamonds. Rock number 1, the tiny diamond signal. This tiny red grain may not look valuable. It is not a diamond. It may not be transparent, and by itself, it may be worth very little. But here is the question: where did it come from? Certain varieties of garnet, especially pyrope-rich garnets with particular chemical characteristics, can become important indicators in diamond exploration. Other indicator minerals can include chromium diopside and certain ilmenites. These minerals can survive weathering, they can be transported by water, and they can become concentrated in sediments. Imagine a volcanic body exposed at the surface. Rain attacks the rock. Rivers remove lighter material. Heavier minerals remain. Over time, the original source can become difficult to recognize, but the minerals it released may continue moving through the landscape. A tiny red grain may have traveled a long distance. Its presence does not prove diamonds, but its chemistry may reveal information about the environment from which it came. So geologists ask, what other minerals are nearby? How far could the grain have traveled? Does the chemistry match a deep geological source? Do multiple clues point in the same direction? A single indicator mineral is only a clue, but a pattern can become evidence. Multiple indicator minerals, compatible chemistry, the right geological setting, the right regional history. Together, they can point toward a possible deeper source. You do not always find the diamond first. Sometimes, you find the evidence that tells you where the diamond may be, and that tiny grain can become the beginning of a much larger geological investigation. The cavity opens, the camera descends into the mantle, the saw cuts through ironstone, silica moves through volcanic fractures. A tiny mineral grain is traced across a map. 5 ugly rocks, 5 different geological processes. The first hit a chamber, the second carried evidence from deep earth. The third preserved a gemstone seam. The fourth revealed the geological recipe behind volcanic opal. And the fifth turned a tiny mineral grain into a possible exploration signal. That is the real lesson of prospecting. Not every unusual rock is valuable. Not every dark rock contains diamonds. Not every volcanic rock contains opal. And not every colorful mineral is rare. The ground does not promise you treasure. It gives you evidence. The better question is not, does this rock look valuable? The better question is, why does this rock look the way it does? Where did it form? What minerals are associated with it? Was it transported, weathered, altered, fractured, filled by mineral-rich fluids, or carried upward from deep inside Earth? Those questions are more powerful than appearance, because sometimes the gemstone is not the most valuable thing you find. Sometimes the most valuable discovery is the clue that tells you where to look next. 5 ugly rocks, 5 different geological stories. One may hide crystals, one may carry mantle material, one may contain a seam of opal, one may preserve the conditions that created precious opal, and one may be nothing more than a tiny mineral grain waiting to be understood. That is the difficult part. Geology does not promise you a treasure, it gives you evidence. And the better you understand that evidence, the less often you walk past something important. Because somewhere, right now, there may be a rock that looks completely worthless, a rock that thousands of people have already ignored, but beneath its dull surface, or inside its chemistry, there may be a geological story waiting to be discovered. Not necessarily a diamond, not necessarily an opal, but something almost as valuable: information. Because once you learn how to read the rocks, the ground beneath your feet never looks ordinary again. So the next time you find an ugly rock, Don't ask only, what is it worth? Ask, what happened to it? Because that question may be where the discovery begins. Pro Gems. The hidden language of rocks.